Hello everyone. This video is about the review section of chapter 1. So first, let's review it section by section. Section 1.1, functions for representations. So in this section, first shows you what is a relation, and the key part is about the function. Function is a rule that assigns exactly one output value, so exactly one y value to the x value. This is a function. So for example, this one is not a function because if you draw a vertical line, so you can see actually for each x value we have two corresponding y values. So this one is not a function. Based on this definition, this is not a function. And this part shows you the vertical line test. This is just the vertical line test. If you draw a vertical line and move it to the right or left, there's only one intersection. But for this one, we have two intersections. So this is not a function. But like this one, if you draw a vertical line, move it to the left or right, we always have only one intersection. So this is a function. So we use the vertical line test to test if a relation is a function. And for the function, we have four representations. First one, numerically in the data table, algebraically as an equation, verbally a description, or graphically. So graphically is just they are graphically. And so I'm gonna show you what we are gonna just talk about one example. Example 2D and 2E. So 2D and 2E, this one asks you which kind of representation it is. So for this one, we have no equation, just a description. So this one, D, is a verbal. And for E, let's see, even though E is still a paragraph, but the key point is actually here, an equation. So as long as you see an equation, it's just an algebraic representation. So this one is a this one is a verbal, but this one, because we have the equation, so this is an algebraic. And so this one shows you the function is like a black box. It's right here, the rule f, and this is the input. For each input, we have a corresponding output, and you have to include the unit. And then next page, a sentence of interpretation. And this one is about a sentence of interpretation for an ordered pair. So what is an ordered pair? Example D, this is an ordered pair, 0, 80. And rewrite it as using the function notation, that is f of 0 equals to 80, p of 0 equals to 80. And the sentence of interpretation of 0, 80 is, so what does 0 mean? 0, let's go back to this question. X, the input variable. X is the number of years since the end of 1990. So 0 just means 1900. And the output is just the US population. The unit is million people. So 080 just means in 1900. The output description, I forgot to say this one. A sentence of interpretation of an ordered pair, we have to first talk about when, and then what, then how much. For the how much, you have to include the unit. So 1, 1980. What means the output description. The output description is the US population. And then what's how much? 80. Do not forget the input unit, that is million people. So 80 million people. So actually, I recommend you, as you watch the video, so when I talk about some specific questions, so you can pause the video first, cover the solution and try to do it by yourself to see if you still remember this definition or this method. So because review section, I'm not gonna teach everything. I'm just gonna try to use the just a couple of minutes to go through all the definitions and just give you several examples. So because sometimes when you watch the video or when you just look at the solutions, you understand everything. But when you try to do it by yourself, then you may notice, all right, here I start here, why? And try to solve it by yourself, then you know where you don't understand. So my suggestion is do not just look at the solutions. Try to solve it by yourself. All right, and then so example 4, we are given this function equation g of t, and this one asks you to evaluate g of 4. So in the calculator, so this one shows you check that the calculator is set to the float and turn off the plots. So this one tells you, this instruction shows you mode. First, click on the mode, and then hit enter to make sure it is float. Float is right here. And then, all right, if you want to draw a function graph, for example, if we have y1, y2, we have two functions. So if this equation is highlighted, for example, y1 is x squared plus 2, and the y2 is 4x plus 3. And if we only want to draw the first function, so just make sure the first, this one, is highlighted. This equation is highlighted. If both of them are highlighted, then you are gonna see both of them on the function graph. So just highlight the function that you wanna draw. All right, and then this one shows you how to enter the equation into the function editor. So y1, this is the equation. And if you want to evaluate the function, just use the variables in the calculator VARS, then YVARS, hit function. So we are going to use the y1. So y1 of 4, that is just the f of 4. This is the similar one. And next one, this is the second method. All right, so this is the key part. How to solve for an equation. So for example, if we are given a function equation, example C, page 6, example C. All right, so if we are given a function equation, this one, and ask you, this is the function equation, and ask you when the function is 10, what is the corresponding t? So that means just try to solve for this equation. What is the value of t? And for this kind of question, we have to use the math solver. So first, make sure you have this is your y1, and then we use math, hit 0. That is math solver. So for math solver, right here, after you use math, you can see this one. Then we click on the solver. So try to solve for the equation. We have two different ways. The first one is y1 equals to 10, and the second one is just 0 equals to y1 minus 10. They are the same thing because we are trying to solve for this is y1. This is the right hand side, the number is 10. And then you can see here, before you hit alpha and enter, we have an initial x value. This is, pay attention, this is not the solution. This is just if you don't change it, normally it is set to 0. If you don't change it, that means, all right, we are going to find the solution that is the closest solution to 0. So, but actually you can change the number here. If you change it to like 900, then after you use alpha enter, the answer you get will be the closest number to the 900 here. So, but because sometimes the function may have multiple solutions, so you can change the number here to find different solutions. And then see here, this is finding a second solution. Now we change it to a -2. Then you can see this time we have a negative solution. Last time we have a positive solution. All right. So next part is about how to sketch a graph. So you can see here for this function we have a domain that t is from -20 to 5. Graphing on a specific domain that is from -20 to 5. So first we use the window. For the window, after you hit the window, you can see this one. Do not change the y value, only change the x value. So set the window, our domain is from -20 to 5. So set it to x minimum is -20, x maximum is 5. And then we use zoom 0, or that is zoom feet. 0 just means feet, zoom feet. Then you can see this is the function graph from -20 to 5. Then, next page example 5. So try to finish example 5. And this part shows you the second method. That is to track the interception. You can just follow these instructions and try to finish example 5. Example 5, the answer is 2.773. So I think because I have given you all the solutions, all the answers, so you can just pause the video and pause the video and finish it if you don't have your textbook with you. And then example 5, this one. All right. So this is the function equation. And try to example 5 is a very good exercise. And try to use math solver to solve for the equation. So just this one, pay attention to the unit. This is 220 million people. But let's go back to check the input unit. It's just a million people. So for this one, example 5, we have to solve for P of according to the function P. All right, this is P of the input. P of T is 250. You have to use 250 instead of 250 million people because the input unit is just a million people. Then solve for this one. And the solution should be in year 1989. After you use math solver, the answer should be about 88.217, but you have to use the next one, next year, 1989. So this one shows you have to be very careful about the unit, because if you use 200 million instead of just 200, you may get the wrong answer. And next, please pause the video and try example 8. So for example 8, and this one is 1.880, and next one 1.386, and this one is negative 2.599. Oh, okay, I forgot the example 9. Example 9 shows you all right, now we have two solutions. How can we get the two solutions? So this is an exercise for two solutions. All right, the next section is about function behavior and the behavior limits. So the first part talks about the direction of the function. The direction, when we talk about the function, we talk about the two parts: direction of the function and the concavity, and the curvature of the function. For the direction of the function, increasing, decreasing are constant, and for the curvature, is either concave up or concave down. And this part we talk about the inflection point. Inflection point is the special point for a function where the concavity changes. And then example 2. Example 2, for example, this part is concave up, this part is concave down. So this is an inflection point. And the end behavior of the function. So the end behavior, for example, if we are given a function like this one, the end behavior is, you can see we have two tails. So these are the end behaviors. So let's see. End behavior of the function describes the output values of a function as the input value either increase or decrease without bound. So this one means when, for example, this is x, this is f of x. This one just means when x goes to positive infinity, that means x increases without bound. And the decreases without bound, similar as x goes to negative infinity. And then the corresponding f of x, the function value, is actually called the end behavior. It can be estimated by evaluating the function at increasing either a very large or very small input value. So that means, all right, we choose this point. So because for this one, the input value is very big. Then let's check the corresponding output values. And this process is actually called the numerical estimation. And then this part talks about the limiting value. So the limiting value after we talk about the end behavior, so we have this notation: limit x goes to positive infinity, that means x goes to this direction. And then if this one is a number, that means L just means it's not positive infinity, it's not the negative infinity, it actually stays the same. This is not a very good example. So for example, let's try this one. So you can see when x goes to infinity, the corresponding f of x stays the same, then we can use this notation. So that means when x goes to infinity, the corresponding f of x stays the same. And then this L is actually called a limiting value x. And then this behavior, this function behavior, you can see actually we have a horizontal asymptote. So this is a horizontal asymptote, and the notation is y equals to L. So pay attention to the horizontal asymptote. For the horizontal asymptote, this point, for example, is 0, 10. Then this point, the y value should be always 10. So that means actually they share the same y value. So that's why we have to use the y equals to something instead of x equals to something. So for a horizontal asymptote, we use y equals to something, and for a vertical asymptote, we use x equals to something. And this part, these two notations indicate that you can see instead of using a specific number, if we use positive infinity, then that means alright, the function value does not stay the same when x goes to infinity. That's like this one. When x goes to negative infinity, you can see the function value actually goes to positive infinity. So for this part, we can use this one, and for this part, we can just use this one. X goes to negative infinity, f of x goes to infinity. Alright, and then let's try to finish example D. This is the question. Alright, you can see we are given this function equation, and then try to finish example D, E, F. So for D, this is just the function value. Then finish D, you can see, alright, we got 186.999, 187.000, 180. And then the other side, this one is x goes to infinity, and the other one is x goes to negative infinity. So you can see when x goes to positive infinity, this numbers here is actually increasing, and this is a very big number. When t goes to negative infinity, so you can see this is decreasing and goes to negative infinity. But here we can see a pattern that is the c of t actually stays the same, 187. So that means that, alright, this function, we have the limiting value t, and this one is the same. And next one, using the limiting notation. So the limiting notation from the left table, we know limit when x goes to positive infinity, c of t, it's just 108.00, because you can see it stays the same. And then similar, this is just the limit x goes to negative infinity, c of, excuse me, this shouldn't be x, this is t, because the input variable is t. So t goes to and then the corresponding c of t is just 156.00, excuse me, 108. Alright, example 5. Write the equation for the two horizontal asymptotes. The second kind of question you may see is like, alright, if we are given this table, we are only given this table, then what kind of asymptote can we get? Horizontal asymptote or vertical asymptote, and what are they? So for this one, you can see, alright, the function value stays the same. So actually, if you try to draw the picture by yourself, you can see, alright, when t is 10, it's right here, it's 181. For example, this is 1. And then when the x goes to infinity, you can see actually the function value stays the same. Then we have a horizontal asymptote. So the two horizontal asymptotes is just one, y equals to 187. The other one is y equals to 158. And then example 4, so you can see this one. When x goes to negative infinity, this direction goes to infinity, and this one is negative infinity. The number of horizontal asymptote is 0. And similar, this one is also 0. Pay attention to, this is not a horizontal asymptote. This is just a horizontal line. For the horizontal asymptote, it must be like this one. You can see this is a horizontal asymptote. This one is not. So you can compare them. Then you can see the difference. So the horizontal asymptote of this one is 0. And the next one, this one, the horizontal asymptote of this one is just 2. Because this is the first one and this is the second one. Alright, this is about section 1.2. So for section 1.3, limits and continuity. So for this one, first, it's about the left-hand limit. Left-hand limit is just for example, this is point C. When x goes to from negative infinity to the point C, so actually that means we approach point C from the left side. So in the notation here, x goes to C minus, that means we are going from negative infinity to point C from the left side. And if the limiting value exists, then it's just 1. And then similar, we have the right-hand limit. X goes to C plus. C plus just means we go from positive infinity, or we go from the right side to C, to approach C. And then this is the left-hand limit. So this part talks about if the limit, so now we are not talking about the left-hand limit or right-hand limit, just the limit. The limit of a function as x approaches C. So no plus, no minus sign. We say the limit of x when x the limit of x when x approaches C exists if and only if. So they are the this is the if and only if condition. So if you wanna say this one exists, you have to check whether this condition is correct. What kind of condition we have to check is you have to check if the left-hand limit equals to the right-hand limit. If the left-hand limit equals to the right-hand limit, then we say the limit of f as x approaches C exists. And then the function notation is just alright. X goes to C, f of x is just L, and this L is actually the left-hand limit, or you can say it's the right-hand limit because they are equal to each other. And this one shows you a vertical asymptote. So last section we talk about the horizontal asymptote is just horizontal asymptote, but this one talks about the vertical asymptote. So for vertical asymptote, if left-hand limit is positive infinity or negative infinity, or the right-hand limit is positive infinity or negative infinity, then the function graph has a vertical asymptote. The vertical asymptote is the equation is just x equals to C. Remember, for the horizontal asymptote, we use y equals to something. So for the vertical asymptote, from here you can see it's so x equals to something. So for this one, we are just going to talk about example 1. For example 1, f of 1, this is 1, f of 1. So we have two, if you try to draw a vertical line, we have two intersections. But this one is a hole. That means the function is not defined here. We have to find the point. So the function value f of 1 is just a 3. And then for example B is about the left side limit. Example C is about the right side limit. So from here you can see actually we have two different ways to show you what is the left side limit. The first one is just by using the function graph. So 1 minus, this is point 1, and 1 minus, we have to use this branch because it goes from negative infinity to 1. Then you can see it's actually negative 2. And similar, 1 plus is just we use this branch, it's still minus 2. So no plus, no minus sign, just 1. So we have to check if the left side limit equals to the right side limit. Both of them are negative 2, so the limit exists, it's just a negative 2. So this is the first method if you are only given a function graph. And the second kind of question is, alright, instead of giving this function graph, you are only giving this table. So make sure you understand why they are the same thing. So if we are only given this table and x goes to 1 minus, so you can see here, 0.9, 0.99, 0.999, all of them are actually approaches 0.1 from the left side. So this is the left side limit. And then let's see the corresponding f of x. You can see actually the f of x goes to 0.2, negative 2. So it's getting closer and closer to negative 2. So the limiting value, the left side limit is just negative 2. And then similar, this one approaches to negative 2. So the right side limit is just negative 2. And then the limit is just negative 2. Example 2. Alright, so this one, Example 2, first f of 3 is just a 20. 3 minus is just a 32 because we have to use this one. And 3 plus, we have to use this one. Then it's 20. So you can see this time, the left side limit and the right side limit, they are not the same. So we have to say the limit does not exist. And then the next one, f of 4 is just a 16. Left side limit is just a 6. We have to use this part. It's just a 16. And the right side limit is this part. Is also 16. So the left side limit and the right side limit, both of them are 16. Then the limiting value exists, and the number is 16. Next part, for the continuous function, we say, for this one, we say a function is continuous at a single point if and only if the 3 conditions are satisfied. The first one, the function value must be exist. So f of c exists. And the second one, the limit would exist. This one just means, alright, the left side limit equals to the right side limit. And the last one, because 2 shows you the limit exists, then we have to check the limiting value is just the function value. If all the 3 conditions are satisfied, then we say the function is continuous at the single point c. And let me see. Example 5. So let's try to do example 5. Example 5, graphically estimate the function value. The value for the function f. F of 6 is right here. So the function, when you try to draw this one, you can see we have only one intersection, that is right here. So f of 6 is just a minus 1/2. And the limit, this one, 6 minus, say this is 0.6. 6 minus, we have to use this branch. So it's just a negative infinity. And the other one, 6 plus, we use this one. So it's just a minus 1/2. And this one, the limited value does not exist. Because the left side limit is not equal to the right side limit. And then this one should ask you why the function is not continuous at 6. So for the continuity, we have to check the 3 conditions. The first one, the limiting value, the function exists. The function value exists, right? Because this is the function value. Second, we have to check the limit. This one exists, does not exist. The second condition is not satisfied. So the function is not continuous at 0.6. The next one, f of 0. F of 0, you can see here we have only a hole. Then it's just undefined. And left side limit is negative 0 minus. So it's just minus 1. And similar, the right side limit is just minus 1. So the limiting value is minus 1. And explain why the function is not continuous at this point. That is because, let's check the first condition. The function is defined, but the function is not defined at 0. So the function is not continuous because the function is not defined. And the next one, this is the optional part. Just ignore it. So next, section 1.4. Section 1.4, linear functions and models. So the first part, a completely defined model. A completely defined model is a statement that describes the relationship between an output variable and an input variable in the context. So you have to include the following 4 parts. The first one, so as long as you see a completely defined blah blah model, you have to, first part, you have to include the equation. And then second part is the output description with units and the input description with units. And then do not forget the data range. And input the data range to describe the interval of data used to find the model. And next one talks about the extrapolation and the interpolation. Extrapolation refers to the use of the model to predict. The keyword is actually outside the input data range. Then we say this is an extrapolation, and the interpolation is inside, is within the data range. And the linear function, so the second box shows you the linear function. A linear function is an equation ax plus b. So for a linear function, the function graph is a line with the slope a. And in the last section, we talk about the concavity of a line. A line has no concavity. And for this one, when you plug in x equals to 0, then we have b. And the value b is actually called the y-intercept, or we can say this is the initial value. And the function, the property of a linear function is the function has a constant slope. The slope is a. The function has a constant slope, and so the function has a constant rate of change. So this is a interpretation for the slope of a line. So you have to include the three parts. First, what? That is the output description. And then you have to say increase or decrease. It depends on the value of the slope. If the slope is negative, then we have to say decreased. By how much? By how much you have to include the unit. The slope unit is actually output unit per input unit. And then the last part. Oh, excuse me, this is the four part. This one has the four parts. The last one you still have to include the domain of the function. So let's see example 1D, 1C. So example 1, this is example 1. 1C, find the slope of the linear function. So for this one, we are given 2 points. The first one is 0, 12,000, and the second one is 80. So if we are given 2 ordered pairs, then you can just use the formula f of x2 minus f of x1 divided by x2 minus x1 to get the slope. So for this one, it's just a 0 minus 1. 12,000 divided by 8 minus 0, and then we got minus 1,500, and the unit is just the output unit, which is dollar. Input unit is a year, so output. So the unit is just dollars per year. And for the interpretation, what is actually output description. That is the resale value. So the interpretation will be the car's resale value, and then increase or decrease. So it's decreased because it's negative. So the car's resale value decreased by how much? By this one. You have to include the unit. So by decreased by negative $1,500 per year. And the next one we have to by how much? 1. Over an 8-year period since it was purchased. Oh, excuse me. Yeah, that's right. All right. So next one, write an equation for R of t. So equation for R of t, we have to use some. All right. Let's just finish it. E, because E covers D. So the formula is, the equation is just R of t equals to minus. And this is a completely different model. So the equation gives the output description, which is the value of a car. The input description, t years after purchase. And you have to include the domain, that is from 0 to 8. So let's see example 2. Example 2, the example 2a shows you how to enter the data. Example 2a will a scatter plot of the data. So if we are only given this data table, how can we get this one? First, in the calculator, we use STAT. After you hit STAT, we choose the first one, edit, and then you can see we have L1, L2, L3. L1 is just the column of year. This is L1, and L2 is just this one, so L2. Now, after you have L1 and L2, like this table, after we have L1 and L2, we are done with the first part, entering data. And then the second step is how to graph it. For the graph, we use the second y equals 2. So second y equals is just the STAT plot. And then you have to make sure the plot 1 is on. Make sure this is highlighted. And then just hit enter. So normally this is X list is set to L1 automatically. You don't have to change it. But sometimes it's L2, L1. So you have to make sure this is L1, L2. If it is L1 and L2, don't change it. And then hit enter. So choose y equals 2 to make sure that everything is empty. If it is not, just clear it. Then we use zoom 9, which is zoom SDAT. Zoom 9, zoom state. So we have this one. You can see this is the scatter plot, which is just what we want. All right, and the next one. So this instruction shows you how to get a scatter plot in your calculator if we are only given the function table. So next one, example E. Wait, 24. Example C. So now, if we are given, from this scatter plot, that we can see actually the function is probably a linear function. So how can we get the function equation of the linear model? Then this one shows you how. Finding and sorting linear function to model data. Still, 3 columns L1 and L2. We have the corresponding input and the output variable, input and output value. Then similar, this one we use SDAT and use number 4. That is a linear function. And then we have this one. So this one shows you the model is ax plus b, which is a linear function, and the corresponding slope is right here, and the y-intercept is this one. So this is the function equation. So next, let's check how that is the model a good model. So that means let's try to put them on one graph. So we use y equals 2 to verify the unrounded model. So this is called, you can see this is called the unrounded model. That means this is the unrounded model. Sometimes, for example, in some web assignment, if you use 3 decimal places, then that kind of model is not the unrounded model. So sometimes you have to use the unrounded model. And then we use zoom 9. So you can see, all right, we have this one. Or this shows you the second method. And 25 example, D and F and G. So this is an exercise of interpolation and extrapolation. The keyword is 2005. So let's go back to check the domain. So you can see this is a domain. 2005 is right here. So this is an interpolation because the 2005 is the inside of the domain. And then what about G? 25. So F is the interpolation. And G, try to finish G as an exercise. For this one, you have to use math solver. So it is just in 2010. Because the solution is 2009.389. So you have to use the next year, that is 2010. And next page shows you how to align the data. This is straightforward, just swap the 2 columns. And then exercise 3A. Try to get the model and finish A. A is you have to write the full completely defined model. Here I'm not gonna show you the solution because alright, I assume everybody has the solution, but in case you don't have it, I just gave you the equation. M of x is just 3.683 x plus. This is the model. And alright, next part, let's go to section 1.5, exponential function. Exponential function. So for exponential function, the function equation is a multiplied by b to the x power, and a is the initial value, b is the constant multiplier. And this one shows you what is the percentage change. So the percentage change between 2 points, x1, f of x1, x2, f of x2 is calculated by f of x2 minus f of x1 divided by f of x1 times 100%. So this is the formula for percentage change. And because this is an exponential function, so you can see after you use this formula, the exponential function has a constant percentage change, and this constant percentage change over is this is the very important part. B minus 1 times 100%, and this formula will not be given for the test. You have to memorize it. And this function has only, remember the number of concavity for exponential function has only one concavity. It determined by the number, it determined by the value of A. A is positive, concave up. A is negative, concave down. And this function has only one horizontal asymptote, that is y equals to 0. And the function value, the limiting value, the end behavior determined by the value of b. So for the value of b cannot be that negative. The value of b must be positive. And then if b is less than 1, then it's just 0. If b is positive, it's greater than 1, so we have the corresponding result. And so this is the function graph for exponential function. So for this one, this is increasing, and this one, this is decreasing. So we have only one concavity determined by the value of A. So this one, A must be positive. The easiest example is A is 1, so e to the x power is positive and concave. And then let's see. So this one shows you how to find the model for an exponential function. So this is pretty similar to last section. The only difference is instead of choose 4, this time for an exponential function, we have to use 0. And then you can see still the rest part is the same. Then you can see, all right, the exponential function is a great model for this question. And this one, percentage change. All right, so next, try to finish example 6. Example 6, we are only given the data table and ask you, all right, this is actually a hint. Write an exponential model. So sometimes if we are not given this one, you have to draw the scatter plot first. Try to make the decision, all right, which kind of model is it? But this one we are given is just an exponential model. Then you can just do it by yourself. So the model is just f of x is just 10.420. So this one gives the output description, which is the percentage. So just gives the percentage. So this one gives the output description. But pay attention to the next part because it's after 17, so you have to change it to who are 17 plus x years of age. And then don't forget the data domain, the data range. Data from 0 to 18. Excuse me. All right, and the next part, use the first part to find the constant percentage change. So for the constant percentage change, we just use b minus 1 times 100. And from here, we know this is the value of b. So just use 0.885 minus 1 times 100%. Then it is negative blah, blah, blah. Next one, what percentage of female MySpace users are 18 years old? So for the 18 years old, it's just 9.222%. And for the 20 years old, it's just and both of them are interpolation because it's inside of the domain. Oh, excuse me. The first one is interpolation. This is the interpolation. But the other one is not because our domain is from 0 to 18. This is inside of the domain. This is the outside one. So we have to use extrapolation. This is section 1.5. And then next, let's try to finish section 1.7. And we will go back to section 1.6 later. Section 1.7, constructed functions. New functions can be formed by combining known functions using addition. So this is the function addition, function subtraction, function multiplication, or function division. A new function can also be formed using function composition by finding the inverse of a function. So terms from business and economics. This one shows you what is a total cost. It's just read it. This is not difficult. And the average cost is total cost divided by the number of the items sold. So the revenue is the selling price per unit multiplied by the number of the units sold. And this is the very important formula. Profit, for the profit, you can just use revenue minus cost. So similarly, revenue, if we plus cost on both sides, then we have revenue is profit plus cost. So make sure you understand for example, if I ask you what is the profit, you know it is just the revenue minus cost. And when I ask you what is the revenue, then you know it is the profit plus cost. So revenue and the profit, actually they are similar concepts, so make sure you know the difference. Profit is revenue minus cost. Revenue is actually profit plus cost. And this part talks about the break-even point. Break-even point is the point where the total cost is equal to total revenue, or it is the point where your profit is zero. That means you didn't make any money or you didn't lose any money. And for this table shows you have to check if you want to use the function addition or function subtraction, you have to make sure that the two functions f of x and the g of x, they have the same input description and they have the same input unit. And then you can see f plus s parentheses of x is f of x plus g of x. And for the multiplication, we have to make sure that f of x and g of x, they have the same input description and the units for x. For this one, we have to, after you finish this part, you have to also check that f of x and the g of x, they have identical output unit. The output unit is the same. And for the function multiplication, you have to double check that it makes sense. The output unit must be compatible. And for the function composition, so you can see for the function multiplication, if it is a dot, then that means f of x multiplied by g of x. And then this one, if it is a whole, a circle, then it just means f of g of x. The output description and the unit. So for this one, you just check the you can see this is the inside function. You have to check the output description for g of x is actually the input description of the outside function f, and they have the same unit. So for this one, a good exercise is just the example 1. So I think everybody has the answer. And example 3. Oh, okay, if you don't have the textbook, example 1, the second part of example 1, and example 3. Alright, and E. And this part, the calculation part, shows you how to evaluate a function constructed using the function composition. So for the function composition, you can see suppose the new function is y1 of y2. So you can see first y1 is just the y1, and then y2 is y2. And for the function composition, we generate a new y3. That is, you can see here is y1 of y2. So you can just calculate for y3 of 7. That is the function composition. New function of 7 is just the y1 of y2 of 7. And then this is the second method. The second method, instead of generating y3, we just have y1 and y2. So first we calculate for y2 of 7, and then y1 of the answer. So that means just the y1 of y2 of 7. So actually that is just the y1 of y2 of 7. They're the same thing. This part, the inverse function. If you just swap the input and the output, then we are gonna get the input function. We are gonna get the inverse function. And the horizontal line test, we can use the horizontal line test to determine graphically whether a function is one-to-one. A one-to-one function is a function for which every output value corresponds to exactly one input value. So if the function is one-to-one, then actually we can find the inverse function. So the inverse function, for example, if two functions f of x and g of x, they are inverse functions, then we have f of g of x is x itself, and g of f of x is also x. So we use the horizontal line test. This is one-to-one, but this one is not one-to-one because we have two intersections. This is one-to-one. And example exercise example 6. So this one, what is the function combination? P of d of x. D of x, this is d of x. P of d of x is just 1 over 33. 33x minus 33 plus 1. So for P of d of x means just plug in d of x into x. So we have this one. And then you can simplify it. It's just x minus 1 plus 1. It's just x. And then d of p of x is just plug in p of x into this one. Then we have 33. 1 over 33x plus 1 minus 33. So this is x plus 33 minus 33. This is x. So you can see P of x, d of x, they are inverse functions because P of d of x is x, d of p of x is also x. And next part is about the section 1.8. Section 1.8, algorithmic functions and models. I'm gonna move it to the next video. So this video just stops here. And from the next video, we are gonna start from section 1.8 and finish the rest part of chapter 1. Alright, thanks for watching.